Beams are structural members capable of resisting transverse loads or loads perpendicular to the beam's axis, like this load right here, for example. And this is our beam. Of course, we have something, whether it is the earth or the soil or any supports, so that we can support this load above, right? When this happens, not only is the beam experiences this load, might as well it experiences internal stress or internal pressure due to this load. When that happens, here's what we call shear and bending moment that will happen, right? Most of the part, we want to know how much the shear and the bending inside the beam on every section, especially on every discontinuity. Now, for example, if we have this kind of load, they call it uniformly distributed load, and it is being distributed over the entire span of our beam. Let's call the span of the beam as L and the load as W. And with that, by principle of equilibrium, for this not to move, then the forces acting to it must be equal to each other, must sum up to 0. In here, if that's the case, supports has its reaction because of this load. And this reaction are also the forces based on Newton's third law. For every action, there is an opposite equal reactions. To solve that, we will mark this as B and here as A. So, if we sum up all the moment about point B and equate it to 0, denoting that all the moments acting with respect to point B, say this one, must be equal to all the counterclockwise moments, the opposite directions, right? So here we can say all the counterclockwise must be equal to clockwise. So here, the counterclockwise or the clockwise, let's start with clockwise first. Clockwise moment that is present on our beam with respect to point B here is this reaction force, RA. So let's write it down, RAL. And there is no other force causing clockwise moment about point B. So we will then directly equate it to this W and find the intensity or the resultant of this. We'll just take this entire rectangle as a shape rectangle, and its area is going to be the base times height, wherein our base here is the length and the height is the magnitude itself. So that's going to be W times L. So it's going to be W about this entire L. And when that happens, it becomes point load about the centroid X bar of the rectangle, which is just half of its base. So we can say that that is also its moment arm, L over 2. Now as you can see, this L gets cancelled because that's when you divide this by L both sides, you're gonna have L over L, which is equal to 1, and you're gonna left with W L over 2. And that's our reaction at A. Alright? If you want to know the reaction about point B, you can either sum moment at point A equal to 0 or forces vertical equal to 0. But let's just use moment at A and let some of the forces at vertical as our checking, right? So we do this, we're gonna have RB times L, which is equal to clockwise moment WL times L over 2. Again, this cancels out, leaving us RB equal to W L over 2. So by the drawing we have here, the free body diagram, we can say that the sum of the forces vertical must be equal to 0. And so all the upward forces must be equal to downward forces for this to have an equilibrium, for this not to move. With that, we can confirm that our reaction is correct, or our reactions are correct. And so we have RA plus RB, these are the upward reaction forces, times the magnitude, the resultant, W by L. So we have 1/2 W by L plus 1/2 W by L, WL times WL. So it's indeed, when you have 1/2 plus 1/2 becomes 1 whole, WL equals WL. So with this one, you can say that our reactions are correct. WL over 2 over and WL over 2 both sides. Also, you can see it based on the symmetry of our given. As you can see, our given is the symmetrical about the center. So this area, WL, must be divided by these supports. That's why we have WL over 2 here. And WL over 2 here. Now, if we want to find the internal shear, we will introduce an axis. This is our x. And we will run an x-axis about these sections. Right? This is going to be our x. We will cut this and expose its internal reactions. Of course, when you expose a beam, in order for this beam to balance out these forces, then it must have a reactions, positive in this direction. This is now the internal shear, and this is now the internal moment. The magnitude is W, the reaction is WL over 2. This is X, and this is our original span, L, right here. And we just cut our beam right on this point X. Alright, now to find this shear, right here, shear, all we need to do is again, apply the equilibrium equation. So that shear, all the downward forces, is W. But this time, it's not L, because we cut it right here. It will become X. Wx is equal to, so these are all downward forces, is equal to upward forces, WL over 2. And so B is equal to WL over 2 minus Wx. This is now our shear equation. Now for the moment, our moment will be about this point. Again, all the counterclockwise, this must be equal to clockwise. So the clockwise moment here is WL over 2, and its moment arm is X. And what else? This moment is opposite, right? Alright, and also this one, so we will have M plus this W times X. Alright, and its moment arm is X over 2. This is just the magnitude, and its distance from the point we're taking the moment, or at the cut, is X over 2. So that our M must be WL over 2 times X minus WX squared 2. So this is now the functions, these two, that describes the moments and shear, internal shear, within our span, a given span, with a given load. So if we test that at x equals 0, it tells us that the shear is equal to the reaction itself. At x equals L, it will become 1/2 minus 1, or negative 1/2. In other words, on this point, our shear is negative of this reaction. And for our moment, at x equals 0, since, as you can see here, there are no external moment, concentrated moment, rather a fixed support, then it must have 0 moments here. We can confirm that by substituting 0 here. Or at point, on the very leftmost, it will turn out to be 0. And also at B, here at this point, you can see that when we plug in L here, these two terms are actually equal to each other, so it will turn out to be 0 as well. So if we want to plot that, this as our shear and this as our moment, I'm gonna see that at x equals 0, it is WL over 2. At x equals L, that's going to be negative WL over 2. And so the graph will look like this, a straight line of first degree. Since this is a linear, this is a 0 degree curve, this must be first degree. And so its maximum, alright, second degree, is going to be, how do you find the maximum? First, equate shear to 0. And the location of 0 shear, the bending moment is maximum. So 0 is equal to WL over 2 minus, this WX. And that is 0, this term will cancel out, leaving us x equals L over 2. And so this tells us that the maximum moment, or wherein the zero here as well occurs, is that x equals to L over 2, or just half of the span. Now that we know the location, we could plug in this to our moment function, this one, to solve for the value of the max. WL over 2 times L over 2 minus W over 2 times L over 2 squared. This term will become WL squared over 4, while here it will become W over 2 L squared over 4. So we have WL over WL squared over 4 minus WL squared over 8, making the denominators the same by multiplying 2 over 2. We'll have 8. This one 2 minus 1 is equal to 1 WL squared. And so our maximum moment located at x equals L over 2 of our given beam is going to be WL squared over 8. So just take note of these values. Alright, this right here is going to be WL squared over 8. Over 8. That's it for this video, guys. Thanks for watching. Peace out.